Hello everyone, I am Jiménez and today I'm going to present towards the development of germanium low-cost interdigitated bad contact solar cells for thermophotovoltaic applications. So I will start my talk by giving an insight about why it's useful to use germanium for TPV application. Then I will explain the two main challenges to obtain high efficiency and low-cost germanium devices based on the optimization of the passivation and doping technologies. Afterwards, I will show you a proof of concept with the first diode fabricating for two different doping technologies, and I will end up by summarizing the main conclusion and next steps. In order to select the most convenient semiconductor to be used, we need to take into account the spectrum. In the case of thermophotovoltaic application, the most efficient semiconductors are the ones with low or moderate bandgap, which are mainly 3-5 semiconductor, which in spite of its high efficiency and versatility, they are too much expensive and they require very complex processing techniques. In fact, 3-5 substrate persists at the largest single cost of TPV modules. That's why, in order to widespread the commercialization of TPV devices, we suggest the continuous development of germanium TPV devices, which is the lowest cost alternative with a substrate price that is around 6 times less than 3-5 semiconductors. Of course, to use germanium has its own limits, as for instance its low efficiency. Here in this graph, we can see the record efficiency for different materials using TPV application. As we can observe, although germanium efficiency has increased a lot during the last decade, its record efficiency is still the lowest from all the evaluated material, with an efficiency of only 16.5%. But is this record efficiency close to its theoretical efficiency? Well, the answer is clearly no, and in fact it is well below its limit, since its record efficiency is just the 30% of its thermodynamic limit, which means that there is still very large room for improvement. But how to overcome germanium limits? Well, our proposal is to increase efficiency with advanced cell architecture such as interdigitated contact solar cells with both contact at the real side. This is the most efficient architecture in silicon devices, but it has never been implemented in germanium. It should be mentioned that it has a predicted efficiency in the range of 18 to 25%, which is already higher than its current record efficiency of 16.5. However, this cell architecture implies a more complex manufacturing process, which can be translated in a higher cost. So to enhance efficiency while keeping low cost, our approach is to create the dop region by means of laser doping, which enable a reduction of the manufacturing process complexity by reducing or avoiding the number of photolithography steps, and it also avoids the high temperature diffusion process for doping purpose, which is one of the most expensive processing steps in conventional PV devices. So, which are the main advantages and challenges of our design? Well, the major advantages are that there are no trade-off with the shadowing factor, which allows to have a higher dense metallization pattern at the rear side, which could be especially advantageous in the case of high current densities such as in TPV application. It also allows the development of highly packed TPV modules, and it facilitates the implementation of a spectral control element on the front and at the back side. The challenges are that we need almost perfect front surface passivation, as most of the carrier are generated in the front and have to be collected in the back, and also we need to create high quality selective contacts. So let me start to introduce you our first approach for the fabrication of germanium devices. We start our manufacturing process with substrate cleaning by in situ plasma with hydrogen in the PCVT reactor, where the intrinsic amorphous silicon carbide is deposited for passivation purpose. Then we deposit the spin-on dopant layer by spinning, and we make a soft baking in order to remove the remaining solvents. Afterward, laser irradiation with an steamer laser make the phosphorus to diffuse into germanium, creating an homogeneous emitter. So let's focus first on the surface cleaning and passivation. We have made the optimization of an stack of intrinsic amorphous silicon carbide by changing the plasma cleaning time and the deposition temperature. Here it is represented the effective carrier lifetime as a function of the plasma cleaning time and the deposition temperature. As you can see, for the lowest temperature deposition, we have carrier lifetime very low, not surpassing 50 microseconds in any case, independently of the plasma duration. The effective carrier lifetime increases when the temperature deposition increases, with better result for longer plasma cleaning time, and the best result with more than 600 microseconds of effective carrier lifetime is achieved for the highest temperature deposition, with a very vast influence of the plasma duration, with the best result obtained for intermediate plasma cleaning time, which has been observed to be useful to remove germanium oxide without causing damaged surface. But how are these results as compared with the literature? Well, we have achieved one of the most successful germanium passivation for the same level of doping, and in fact, we have obtained effective carrier lifetime even higher than 1 millisecond when working with intrinsic germanium. In this way, we can see that we have achieved a good enough passivation with estimated surface recombination velocities in the order of 20 centimeters per second, addressing like that the first challenge for IBC cell. Let's focus now on the anti-doping optimization by steamer laser irradiation of phosphorus spin-on dopant. In order to diffuse phosphorus through amorphous silicon carbide, we have used an steamer laser emitted at 248 nanometers. We create relatively large spots by means of a beam homogenizer, and we work at a frequency of 1 Hz. In order to optimize the N-type doping, we have varied the fluence and also the number of pulses. Here in this graph, we can see the phosphorus chemical concentration as a function of depth for samples with different number of pulses. As you can see, as the number of pulses increases, the surface concentration is reduced and the junction depth increases. This is a result of the redistribution of the impurity atoms already incorporated during the first pull. We have also checked the electrical activation by Hall measurement. Here it is represented the electrically active dose as a function of the number of pulses for the two different energy fluences. We have also represent the chemical dose calculated from scenes as a reference. As you can see, both fluencies follow the same tendency with the number of pulses, with the highest level of activation achieved for the highest number of pulses. In terms of fluence, higher activation is achieved for the highest energy fluent condition, where a very similar dose between the chemical dose and the electrical dose is achieved. So we can say that we have almost 100% activation, which means that we have successfully demonstrated the emitter formation with electrically active concentration close to 10 to 19 cubic centimeters. Now that the surface cleaning and passivation and also the doping have been optimized, we can proceed with the metal deposition to create and fabricate our first diodes. Here are the results from the IBQ measurements in logarithmic and also in linear scale of a diode fabricated with the aforementioned doping technology. From the IBQ, we can observe diode behavior as current flow just in one side, but it is not ideal at all. To better understand the main problems related with our devices, we have fit the IBQ with the second diode model, which allow us to find out the saturation current densities, the ideality factor, and also the series and shunt resistance. The results reveal very high saturation current densities and really low shunt resistance. Most probably, these issues could be explained by a damaged emitter, as the high energy fluence is necessary and also high number of pulses in order to create a highly doped emitter. This happens because the doping source, the spin-on dopant layer, is very far away from the germanium surface. Also, it can be related with a very high surface recombination velocity, as the emitter is uniform in the whole area of the device, which can compromise the surface passivation achieved. That's why, in order to be able to use less energetic laser condition, but still to create highly doped region, we have also tried in a second approach to use N-type dope amorphous silicon carbide instead of spin-on dopant solution as a doping source. In this way, the N-type dopant source is the distance to germanium is greatly reduced. In addition, we have also implemented a non-uniform laser dope emitter, which can preserve passivation in the non-irradiated areas. As already mentioned, in this second laser doping approach, amorphous silicon carbide serves for both passivation but also doping purpose. In this case, we have used an ultraviolet laser emitting at 355 nanometer, whose main characteristic is its really small spot size of only 20 micron in diameter. We have chosen this laser in order to be able to create the point contact emitter, and we have fabricated diodes of 9 square millimeter by making an hexagonal matrix of point with spots separated 200 micron between them, as shown in this picture. We have used the same metallization scheme, and we have checked the quality of the diodes fabricated with this second technology. In order to compare the two main doping technologies presented in this work, the homogeneous emitter created by laser irradiation of spin-on dopant sources, and also the point contact emitter created by irradiation of an n-type doped star, here are represented the IV cure of the best diode fabricated with this technology. As you can see, the homogeneous spin-on dopant is represented with a black dashed line, and the point contact pass doped emitter with a continuous blue line. As we can see, the leakage current in the reverse region is much higher for the spin-on dopant approach, and also the saturation current density in the forward bias. So more conclusion can arise from the second diode model fitting, where a big improvement in terms of shunt resistance and saturation current densities are stated. So as the main conclusion are that we have obtained a very high degree of surface passivation in germanium with effective carrier lifetime of more than 1 millisecond for intrinsic wafers and estimated surface recombination velocity of around 20 cm per second. We have demonstrated diode behavior with two different doping approaches based on laser doping, with the best result obtained in the case of the point contact pass doped emitter. Like this, we have addressed the two main challenges for germanium IBC fabrication. Next step will be the implementation of the technology in an IBC solar cell and its characterization in real TPV conditions. This technology is also useful for the development of three-terminal thermogenic PV devices and also for thermogenic enhanced near-field TPV devices, as it will be presented by my colleagues in the next section. Thank you very much for your attention, and I'm happy to take your questions.